Okay, second video on integration by parts. Let's go ahead and jump right in, but let's try one that's just a little more complicated. Okay, and we have x squared cosine 3x dx. That's not overly complicated, but those of you who have done a few of these are already recognizing the fact that x squared, when you take the derivative once, is not going to go away. Okay, so you might actually have to do 2 rounds, is what you might be thinking. And you'd actually be right, okay? So we have u is equal to x squared. Okay, it's not going to go away on the first round, but it's still going to drop down 1 degree, which is preferable to it, not dropping down at all. So that becomes 2x dx. And when I anti-differentiate cosine, I'm going to get 1/3 sine 3x. Okay. And so we go ahead and do this first step, and we're going to get 1/3 x squared sine 3x minus 2/3 x sine 3x dx. Okay? Well, here's the thing. I'm going to need to go ahead and do a second round of parts using this one right here, because I still have a product function in the integrand that is a combination between 2 different families or 2 different classes of functions. And so u is equal to x, du is equal to dx. My dv is sine 3x dx, and my v is negative 1/3 cosine 3x. Okay. Well, let's go ahead and pop it down here. Sine 3x. Now remember, this integrand right here implies the difference. So I'm going to need to distribute that negative 2/3. So let's go ahead and put a bracket. And I get negative 1/3 x cosine 3x plus, and the only reason it's plus is I'm already taking into account that negative right there. When you subtract the negative, it's obviously going to be a positive. Cosine 3x dx. Okay, so we can go ahead and distribute. That cleans this up just a little bit. And I wind up with 1/3 x squared sine 3x plus 2/9 x cosine 3x minus 2/9, but it's not 2/9 because the moment that I anti-differentiate that, I'm going to get 1/3 sine 3x. I've already done that legwork right there, okay? So I'm going to get 2/27 sine 3x plus c. Okay, 2 rounds of integration by parts. That's it's not too fun. Well, what happens if I'm given something where it's x cubed cosine 3x dx? And at this point, the thought of doing 3 rounds of that is just exhausting. Okay. But here's the thing. Anything that is done iteratively like this, you should be able to figure out some way of making up some sort of chart or algorithm or table to actually get this done. Since, what happened up here is it wasn't like once you did it once right here, it wasn't a mystery what you were gonna designate as u right here. You basically took what was left over from the last u and designated it as u again. It wasn't a mystery what you were going to designate as dv. You took what was anti-differentiated into v right here, stripped it of its coefficient, and plopped it down right here as your dv. So if it's predictable what's going to happen in terms of being able to do it over and over and over again, we actually can drop it into what's called a table. And this is integration by parts tabular method. Okay. And actually, let's go ahead and just do it for Let's do it for exactly the integral we had up here. I want to show you that you get the same thing, okay? But it can be used when you get, x to the third, x to the fourth, x to the fifth, whatever, okay? Here, we're going to go sine, S-I-G-N, not S-I-N-E, right? Here, this is u, and here, this is dv. Now, why do we have a column for sines? Well, you got to remember that the formula is u times dv is equal to u times v minus v du. This is a difference. Well, if this one then needs to be done in terms of parts as well, you're going to have to distribute a negative across another difference. And therefore, when you distribute that negative, the next integral is going to wind up being positive. And then, of course, negative again, and then positive again, and then negative again. It has everything to do with distributing that negative across further implementations of integration by parts. So the first time's positive, positive because that first term is positive, and then negative because that next term is negative. And then, of course, the integral that's implied, if you have to do it again, it's going to be positive, negative. So you just start with positive and just start alternating back and forth. Here we have x squared, and then I'm just going to differentiate until it's gone. Up there, it's gone. It's 0 now. Here, I'm going to anti-differentiate down to the same level, okay? And I'm going to get negative 1/9 cosine 3x, and then negative 1/27 sine 3x. Those ought to look familiar. So all I do is I go over, down at an angle, over, down at an angle, over, down at an angle, okay? And so the first term is going to be x squared times 1/3 sine 3x, which is exactly what that is. The second term is going to be negative 2x times negative 1/9 cosine 3x. The negatives cancel each other out. The 2 combines with the 1/9 and becomes 2/9 x cosine 3x, which is exactly what I have for my second term. The third term is going to be negative 1/27 times 2 times sine of 3x, which is exactly what I have for the third term. You can't really have a fourth term because it multiplies by 0, so you're done. You just tack on a plus c at the end. That is what's called the tabular method. And again, some teachers set up their tables so they look a little bit different than this, but it's the same idea, and it's the same pieces of information, okay? And the reason why it goes over and then slants down is that you're not combining u and v. You're combining you're not combining u and dv. You're combining u and dv's antiderivative. Okay, so you have to go over and then slant down to get that v. Because if you just went straight over, you'd be multiplying u times dv. Okay, and then this u, this is v for this u. This is v for this u. So you go over and then slant down. And it winds up being, rather straightforward. Once you get the hang of it. Once you do it like, a couple times, tabular method will be your best friend. And basically what happens is you need to look at it, and every time you see something, if it's x squared, I go ahead and do it by hand. Once it turns into x cubed, you really don't want to do it by hand. Well, let's do something like that. Now that winds up being different than the ones we've done previously, because the ones we've done previously always had a component that was a polynomial. And polynomials, when you differentiate them, at least when you differentiate them enough times, they go away. They disappear because of the power rule. The power rule brings the degree down by 1 each time you do it. The problem with e to the x and cosine x is that neither of them go away. Well, let's go ahead and see what kind of fun we can have anyway, okay? And the only reason I'm designating, and it doesn't really matter which one you do, the only reason I'm designating dv as cosine is I like to stave off the negatives for as long as possible, and I know that if I differentiate cosine, I get a negative in that very first term, whereas if I anti-differentiate it, it goes to positive sine x rather easily. Okay, this winds up being e to the x sine x minus, e to dx down here, e to the x sine x dx. Well, some people might look at that and think of that as more of a step backwards than a step forwards. Well, let's go ahead and do it again. And if you do it again, notice that I'm always designating u by that same class of functions. I'm not going to flip around and designate u as the trig function, and I might get to an example to show you why, but I don't want to burn time right here. But just basically, if u is e to the x the first time, u is e to the x the second time. If u is the polynomial the first time, u is the polynomial the second time. If dv is the trig the first time, dv is the trig the second time. Okay. Now, could I take that negative and absorb it into the sign so that when I anti-differentiate, I don't have to deal with the negative? The negative kind of gets absorbed. I could, and if that's the way your brain works, then go ahead and do it that way. I'm just going to go ahead and do it straightforward. So I get negative cosine x right here. Well, let's go ahead and drop down here, and let's actually do the new parts. Remember, this part is just for that integral, so that first term and the negative come along for the ride, and then basically this right here is basically a reformulation of that second term in that integral, which is the second term. So you get negative e to the x cosine x minus e to the x cosine x dx. Okay? But there's also a negative here, so that becomes a plus right there. That makes sense? Because it was minus, but then there's another minus in the v, and so basically when we distribute that negative out in front, see, that's the only hard part about this, is just keeping track of all the negatives that pop up in your integration and everything else. E to the x cosine x dx. That looks awfully familiar. That looks like the original. So this whole thing is equal to the original. Okay, well, let's go ahead and rewrite that. The original integral is equal to e to the x sine x plus e to the x cosine x minus the integral of e to the x cosine x dx. Wait a minute. Can I just collect like terms and ship that over to the other side? Oh my gosh, I can. Wouldn't that just be neat? So I have e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x. Let's go ahead and tack on a c value right there. We'll call it c1 because I'm about to divide by 2 and get 1/2 e to the x sine x plus 1/2 e to the x cosine x plus, and we'll call it c2 since it's still a constant, it's just a different one from the step before it. How's that for a creative way to do it? Okay, and that is equal to the integral. So the neat thing is you actually didn't wind up having to ever integrate per se, I mean, except for the fact that you were anti-differentiating within these little boxes right here. You didn't ever have to actually integrate that piece that was over here on the right-hand side. It basically morphed such that it could be combined with the original and then just divide by the coefficient. And there you go. Okay. So we have done let's go ahead and let's see if we can do another tabular one. How about we do, how about x to the third times e to the 2x dx. Okay. Well, obviously the e to the 2x is not going anywhere. All it's going to do when you either differentiate it or anti-differentiate it, it's just going to accumulate coefficients because of that 2x that's in the exponent. But I do know that x cubed can be gotten rid of, so to speak. Oops, the only problem with using a pen is they smear. So let's do positive and negative, u and dv. So positive, negative, positive, negative, positive. I know that x cubed becomes 3x squared, which becomes 6x, which becomes 6, and eventually disappears after, 4 differentiation executions, okay? And that becomes e to the 2x. Now if I were to differentiate it, it would become 2 times e to the 2x. But if I anti-differentiate it, the coefficients go the other way. And I'm going to get 1/8 e to the 2x and then 1/16 e to the 2x. And remember, it's over and down, over and down, over and down, over and down. So the answer to this particular integral is 1/2 x cubed e to the 2x minus 3/4 x squared e to the 2x plus, well, 6 and 1/8, of course, reduced to 3/4, so we have 3/4 again, x e to the 2x. 6 over 16 reduces to 3/8, negative 3/8 e to the 2x, and then of course it's an indefinite integral, so we have to tack on the plus c. Okay. In the next video we'll do a couple more examples, including examples of the definite integral using integration by parts. From there we'll move on to the next section. As always, email me with any questions that you have, requests, all this concerns, whatever, and I'll look forward to hearing from you. Bye.